how the cross product is derived, just so that we can kind of put that in context and make it make sense. Okay, completely distracting. Good. So I've got my two vectors, and my x, y, and z coordinate are a1, a2, a3, using subscripts. My second vector b is b1, b2, and b3. So those two vectors together are going to make a plane, right? Okay, or they're going to lie in a plane together. We want to find a perpendicular vector to both of those. So we're going to find a vector u, and we're going to give it the general coordinates x, y, and z. That is going to be perpendicular to both a and b. Good so far? Okay.
Yeah.
Perpendicular to a. So if I take the dot product of those two vectors, what should the result be if they're perpendicular? Remembering what the dot product was.
0?
Yeah,
1?
that's right.
0.
Should be 0, right? Because it's equal to the magnitude of A times the magnitude of B, U, and times the cosine of whatever the angle is. If the angle is 90, cosine 0, so that dot product is going to be 0. Same with this one, should also be 0. So we've already got a little place we can start to try and find a formula that's going to determine the cross product vector. So you're going to see how that whole crazy formula got developed this way. Okay? So does it make sense? That's kind of where it came from?
Yeah.
Okay. So A dot U, A1, A2, A3, X, Y, Z. So when we do the dot product, what's this going to be, RJ?
A1x.
A1X plus, yep, keep going. Luke?
E2 and Y.
Yep. And Mark, our grade 9 student of the day, has just beaten RJ to the punch. Yes, it's A3 times Z, and that's equal to 0. Okay, same thing with this one. It's a perpendicular vector. So that's B1x plus B2y plus B3z. That is also equal to 0. Okay. So this is equation 1, and this is equation 2. Now, what we're going to do is try and use these two equations. We're going to do an elimination on the variable z. To do elimination, we have to have the same coefficient in front of the z in both cases. So I'm going to have to multiply 1 by something, and I'm going to have to multiply equation 2 by something. So I've got an A3 in front of my Z here. I've got a B3 in front of my Z there. What should I multiply equation 1 by so that I get a common coefficient in front of my Z? I should multiply it by B3. That's right. Okay? So B3 times equation 1. And likewise, I have to multiply equation 2 by something. What should that be? Mark?
A3.
A3. It should be A3. There we go. We said calculus was hard, eh? Just go straight from grade 9 into calculus. Okay.
I'm grade 2 still, but kicking in. I see patterns, so I'm just
Yeah, because we multiply multiply both sides.
Alright.
Yeah, we multiply both sides by A3. Okay. So I'm actually going to take number 4. I'm going to subtract number 3 from it. So I'm going to take A3B1x and subtract A1B3x. Okay. And so I'm going to take A3B2y and I'm going to subtract A2B3y. So that whole entire thing is still equal to 0 because when I subtract 0 from 0, I get.
That's what I said. I said 0. You said I was wrong.
Oh, there we go.
I said still ugly.
So,
Yeah, that entire, the two bracket rows. Sorry to hear that. You said it was-
Okay.
is it 0?
I was kind of worried there for a minute. I thought RJ said I was ugly. Right now he's arguing with our grade 9 peanut gallery.
I thought you said, is it easy? I'm like, no, it's still ugly. It doesn't get easy for a while.
I said, yeah.
Okay.
True.
Does that make sense so far, Luke?
Yeah.
Okay. Perfect. We're going to set these up. We're actually going to move this expression over to the other side of the equation and equate it with that expression. So I've just moved it over down to the other side of the equation. Nothing too miraculous there. Okay. When the negative goes through, so we just have to switch signs and swap places. Now I'm going to get these expressions. I'm going to divide both sides by both expressions. So if you want to call it uncross multiplying or something like that, that's fine.
What? No.
Essentially, you're right, Mark. Right? I'm going to divide this side by this expression. So it's going to cancel out. But it's going to end up in the denominator over here. And when I divide this side by this expression, it will cancel out on this side. And it's going to end up in the denominator over here. So that's actually what did happen. Yes, we canceled them out. They were equal to 1. Okay? Okay. Now, I'm not going to do it because it's a kind of a long song and dance, but we can do exactly the same thing with Z, and we're going to end up with an expression in Z that looks like this. So you notice that this already picks up those patterns. So all those things are equal to each other and they're going to be equal to some constant. That constant, we're going to call it C for now. So, we could say that x is equal to C times A2B3 minus A3B2. We can also see that y is equal to C times and A3B1 minus A1B3. We can see that z is equal to C times A1B2 minus A2B1. So we actually have something that's telling us exactly what our x, y, and z coordinates are relative to the coordinates of those first two vectors, okay? And it's just being multiplied by whatever constant we like C. It doesn't matter how long that vector is, it's going to be still perpendicular. Anyways, when you actually work this out,
I'm just getting through this class.
so have we driven away our grade 9s? There we go. So C is equal to 1. So these are the formulas that tell us the cross product. Basically, it's derived from that whole idea that the dot product has to be equal to 0 for those two vectors. Okay? So that's where the cross product comes from. Sound all right? Okay. So this is for a while I always thought that the cross product was maybe a little bit arcane, but actually this is one of the most useful most useful tools in the quiver when you're dealing with electricity and electromagnetic radiation. So it's actually helped us make some of the biggest leaps that we've ever made back at the end of the 1900s to find out basically that there's a speed of light and that electromagnetic radiation is actually a wave and that the electric vector is perpendicular to the magnetic vector. Okay, got a question? Let's find a vector that is perpendicular to 1, 2, and negative 4, and 3, negative 1, and 5. So RJ says, using what we just learned or what was in the preamble, I would say use what was in the preamble because they are actually exactly the same formula. So if you look at those A, B's, and C's, that method in the formula just takes you through the whole. You don't have to technically memorize those formulas. I do expect you to understand that proof though. Okay? Where it comes from.
So we're just finding the vector or the angle?
Actually, just the vector, that's it. Did you get one? Did you get something already?
Yeah, I think so.
Okay. Luke, you go first.
6.
-17.
Negative 17,
And -7.
negative 7. We have agreement. Yeah, right on. Okay, so this vector is perpendicular to those two. Tell me this. Can you give me a second vector that's also perpendicular?
-6, 17, and 7.
Yeah, okay. -6, 17, and 7. It's also perpendicular. So all that RJ did there was he did a scalar multiplication, that's right. So he multiplied by -1. So that vector is actually, if we were to look at it on GeoGebra right now, which would be a good idea, but it would take me 5 minutes to get that all figured out. If we looked at it on GeoGebra, it would be just in the opposite direction. Okay, very good. Okay. So what does that result in? Does that give me a vector or a scalar? Yeah. So RJ votes on vector for A dot B, Luke. What do you think? Is that a vector or a scalar?
Vector.
Vector?
Yeah.
RJ's thinking twice.
Or,
I think it might be scalar, just because it's a single number.
We end up with a single number. That's right. So we say that that gives a scalar. So just a number. That's it. So A dot B is a scalar. So the operation of cross product gives us a vector. Of course, that's as long as A and B are both vectors. Okay, what about that operation there? Is that going to give me a scalar or a vector? RJ's voting now. What do you say, Luke?
scalar.
Luke says scalar,
I say vector.
and RJ chooses vector. Why do you think it's a vector, RJ?
Because the vector, if you take,
RJ says he doesn't know. Why do you say vector, Luke?
that's, he says.
Because cross product gives a vector,
Oh,
and then it's just
Yeah.
vector times vector.
Yeah, so good. This gives you a vector. This is the dot product of a vector.
Dot product, so
And-
it's, vector times a dot product.
Okay, that's right. Very good. Okay. So that's actually known as triple scalar product. And it has an interpretation that we won't be looking at today, which is good news. Okay. So let's do u dot v by another two vectors m cross n. So is that going to be a scalar, a vector, or a meaningless expression? Okay, so tell me, is that a vector, a scalar, or a meaningless expression?
Like, I'm going to go with
I think so.
RJ's chosen meaningless,
It's a vector.
and Luke says it's a vector.
Well, I'm not sure about how you find the perpendicular to a scalar.
Okay, so what are you saying, RJ, that this is a scalar?
Yeah, that becomes a scalar. And M is a vector.
That's a perpendicular vector,
Yeah.
and then scalar
So
cross vector can't be done. Yeah, basically, if we have a scalar, we can't do the cross product. So this one is meaningless expression. So far, this whole thing is tied up. Okay. So vector, scalar, or meaningless expression. RJ says vector. Luke, what do you think?
Yeah, same thing.
You're absolutely right. Yeah. This returns a perpendicular vector to u and v,
And then find the perpendicular.
and then you find a perpendicular vector to that. Yep. Okay, very good. So the last thing, that perpendicular vector actually does have a size. So we can calculate the magnitude. Yeah, so this one is sine. So a lot like the dot product gave us cosine, this one gives us sine. Theta is the angle between the two vectors. So that's just a formula. It's a straight up formula. Now in the CEMC materials, they actually have like a big, long, giant, long proof of why that is, where that formula comes from. Yeah, just take a quick look at it out of interest, just so you know what it looks like. It's very long and involved though. We actually do not have to even, technically we don't have to be concerned about the proof of what the cross product is. But we're going to anyway because we're better. We're better than that. Yeah, just might be on a test. Okay, that's not that hard though, is it? Like the important part is those dot products are equal to 0. Okay, last thing. Hand rules. Okay. So this actually tells us what direction what direction the vector is pointed. So you might remember these from physics because they apply to electricity and magnetism. Okay, so here's A, there's B. Whoa, nice hand. There's Homer Simpson's hand. I guess these are, this is the right hand. So that's our right hand. And this is doing A cross B. So the first vector in that product, in that cross product, that's where our thumb goes on our right hand. Okay? So you can actually hold your right hand up, and your thumb is going to point to the first thing in that product. Okay? Your palm.
So it would be cross back or A. It would be sideways.
So if it's B cross A, if B was first, I'm going to put my thumb
Alright,
in the direction of B, and my fingers in the direction of
so
A.
you can turn your hand upside down.
So yeah, your hand is either going to go that way for A cross B,
Alright,
or it's going to go that way for B cross A. Okay? And the cross product goes in the direction of your palm. Okay, the direction as if you're pushing.
so it would be cross A, you do left hand?
You could, well, if it's B cross A, you take your right hand, your thumb goes out there. Which way is the cross product vector? Out from the board if it was B cross A. And if it's A cross B, it's into the board.
I
Yeah.
just want to your right hand.
Okay.
Or is it always with your right
It's
hand?
always with your right hand to make that work. Okay. So your thumb goes with the first vector, and cross product is in the direction of your palm. So this is going into the board. So B cross A would go out. Oh. We've got somebody else. I think it might be Brianna. Here we go. Okay. That's that. So I think I assigned like 1 to 8 in the exercises. So they're pretty fast. They're pretty easy to do. You've got two choices. You could actually make this on a spreadsheet to make it like so that you get the calculation right every time, or you could even get GeoGebra 5. It'll do your cross product for you. Okay. All right. Is that all right, Luke?
Yeah, that's good.
Okay. Good. RJ, is that all right? Okay, good. So try 1 to 8 tonight, and tomorrow we're just doing applications of cross and dot product. So there's just some area volume questions as well as torque. So,
Okay.
okay,
I'm working on the assignment,
Good.
and did we ever do like a lesson on optimization or anything?
yeah, we did. Yeah, were you here for that? Oh, you know what? Yeah, we did the boxes, so we did do some optimization stuff. Do you have some specific questions?
No. Well, there's some examples in the CMC, so
Yeah.
those will help me.
Okay. Yeah, let me know. Like, I gave that as an assignment and didn't really put anything on a test. The hardest part about all that, the hardest part about the optimization is making the formulation. So, for example, there's the cutout box. So, you've got I don't know, a 20 by 10 sheet, and you're going to cut little corners out, and you need to figure out, what is it? You need to figure out the maximum volume that you can get. So, so that's an example, right? So we need to figure out what the volume is. So we just say, this is our quantity that we're going to maximize. This actually provides the constraint for us here. There's Megan.
Sorry,
Late.
I'm going home, but
Okay, all right. We've just got a question about assignment 4.
I haven't looked at it.
Megan hasn't looked at it. So say congratulations to Megan. She won silver in at Canada-wide Science Fair.
Oh, congrats! That's good.
Thank you.
Yeah, she did pretty good. So, Megan, were you here for the optimization lesson? I think it was
I think
Megan.
it was just
Megan was here. It was just
RJ abandoned me at one point.
yeah. RJ took off, and so that Megan's getting even by only working from home. Okay. So, what's the ordinary equation for volume? Because this is the one we're going to optimize.
I come to the top 10.
Length times width times height. That's right. And I'm
And
using
you just said
x.
what's in it.
Did I say width? Okay. I did that on purpose.
Did you?
Okay. So we're gonna cut out.
So width squared.
We're gonna cut out a little corner, and it's gonna be x by x. Okay. So this is how you formulate it. We have to get our equation completely in terms of a single variable. So volume has to be in terms of x only. So
Or length times width minus x squared.
okay. So what's my length once I cut this x out and fold it up? It's 20. My length is 20 minus, and that 20 minus x is wrong.
Minus 2x.
So my length is 20 minus
I didn't know
2x.
you took it out of each part, I thought you wanted to take it out of the one part.
That doesn't make any sense.
That
Oh,
doesn't
the
make
box!
You wouldn't have a box. And then what's my width?
10 minus 20.
10 minus 2x. And then when I fold it up, what's the height of the box going to be?
X.
X. That's right. Okay. Anyways, what you do is you're going to take the derivative of that, and you're going to try and, hey, take the derivative and set it equal to
0.
0. Yeah, because we're trying to find the maximum. Yeah.
Oh, okay.
Okay? They're all like that.
All right.
Okay.
Thanks.
Okay. Yeah, if there's any other questions, see you, Meg. Okay. All right. So I guess we'll see you tomorrow. Will you be able to make it tomorrow, Luke?
Oh, yeah, I should.
Okay. Perfect. And if you have any other problems with the assignment, just ask tomorrow.
Sounds good.
Okay, we'll see you.
Alright, see you guys.
So I was looking at the chat, what was, Brianna added? So it says you added me and Megan, and then you added Luke and Lee, and then she joined.
Oh, I had to send her a link actually.
Alright.
Yeah.
She just joined like randomly and must, I said